Modern laptops routinely perform incredibly dense calculations. They stream high-definition media, render complex software, and train artificial intelligence models, and connect billions of people across the globe in real time. Inside the machine, there is no inherent concept of video, no recognition of color, and no capacity for language. At the base of the hardware, the computer only encounters two physical states: electrical current flowing or electrical current blocked. Engineers map these states into a numerical language. A flowing current is a 1, a blocked current is a 0. This is the binary system. The primary question is how a simple electrical pulse physically translates into a photorealistic galaxy on a screen. The answer lies in abstraction. By stacking simple physical mechanics on top of each other, layer by layer, engineers build an intricate digital world. If we strip away the exterior, we find billions of tiny electronic components called transistors etched into the silicon. A transistor acts as a microscopic physical switch. When the switch closes, electrical current flows through the circuit. When it opens, the current stops. Relying on just two voltage states makes the hardware reliable. It is easier to detect whether a wire has voltage or not than it is to measure 10 different subtle levels of electricity without making an error. While a single transistor flipping between a 1 and a 0 does very little, the capability of the machine emerges when these switches are wired together. When two transistors are placed in a row on an electrical line, they form a logic gate. Because they're in sequence, the first switch and the second switch must be closed for current to pass. If both inputs are 1, the output is 1. Chaining millions of these gates together allows the circuits to perform base 2 mathematics, executing addition and multiplication through physical logic. Every calculation is the result of routing electrical currents through sprawling physical mazes of logic gates at incredible speeds. To bridge the gap between microscopic electrical mazes and the human experience, we need a way to translate raw voltages into information we can perceive. This is a byte, a sequence of 8 binary bits. Because each bit has two states, grouping 8 together mathematically provides 256 unique values. We encode text by assigning patterns to specific characters. The sequence 01000001 translates exactly to the capital letter A. Visual media follows the same principle. Screens are grids of pixels assigned numerical color values. Each color is a mix of red, green, and blue light, represented by numbers from 0 to 255. Sound is captured by measuring the physical amplitude of a sound wave thousands of times a second and storing those measurements as binary numbers. The central processing unit, or CPU, drives this translation. It fetches massive sequences of 1s and 0s from memory, decodes them, and routes electricity through the appropriate circuits. Even software code written in Python or C++ is eventually compiled down into machine code, the raw binary instructions that the processor can physically execute. Text, video, and audio are all complex mathematical translations, standardizing reality into uniform sequences of 1s and 0s. When you use a laptop, you are interacting with the very top of this layered system. You interact with the interface without needing to consider the billions of microscopic switches flipping underneath your fingers. These distinct layers allow us to interact with the screen using our native languages, instead of the machine's native voltage. Even the most advanced neural networks rely on this foundation. If you scale down and zoom in on a single node, you will find binary computation at the floor. This illusion depends on billions of transistors executing billions of operations every second just to keep the screen active. The entire digital world ultimately emerges from simple physical switches flipping between on and off in the dark.